In this video, we're going to work on the calorimetry of ideal gases. We're going to try to understand their specific heat capacities at constant volumes and constant pressures. So we can look at a pretty simple question to help us approach this topic. If we wish to raise the temperature of 1 mole of monatomic ideal gas by 10 degrees Celsius, which process will require more heat energy? Will it be a constant volume, a constant pressure, or will they just require the same? So let's break it up and look at each process individually. So let's look at the constant volume process first. So we have a constant volume process, and we should review that we can accomplish this by locking the piston. So there will be no displacement of the piston, and therefore work will equal 0. So in the first law equation, delta ETH will just equal Q. Because, like we just said, this W is equal to 0. So now you're saying, well, we're looking for this Q, and knowing that it's going to equal the change in thermal energy, that doesn't really help. But we can maybe figure something out about this change in thermal energy if we consider that the thermal energy is equal to N, which is just the number of particles, times the average kinetic energy of those particles. So that's going to equal N times 3/2 times Boltzmann's constant times the temperature. And Boltzmann's constant, that's really just the gas constant R over Avogadro's number, which is right here as Na. So now we can see, we can just simplify this a little bit. So we have 3/2 the number of particles over Avogadro's number times the gas constant times temperature. So we can simplify this to 3/2 times the number of moles times the gas constant times temperature. So it would follow that the change in thermal energy will equal 3/2 times the number of moles times the gas constant times the change in temperature. So now that we have this expression right here for delta ETH, let's plug it back into this. And we'll see that Q equals 3/2 the number of moles are changed in thermal energy. Okay, so if we start to plug in what we need to here, we'll see, well, it's 1 mole, and the gas constant should be 8.134 or something joules per mole degree Celsius or Kelvin. And in this case, we're raising it by 10 degrees Celsius for our delta T. And that's going to come out to be something like 122 joules. And you can check that if you'd like. So now, let's go ahead and give the same treatment to our constant pressure process. And just to review, constant pressure process, we're going to allow the piston to slide without friction. And for this one, we're going to have a little bit of a harder time simplifying this first law equation. So here, we just see that delta ETH equals work plus Q, heat transfer, and there is going to be work this time. So let's go ahead and start working through this. And will it be the case that the change in thermal energy will equal 3/2 NR delta T? Yeah, it still will. And we have W plus Q over here. So we want to find this Q, but we have this pesky W to deal with. And so we might say to ourselves, well, we remember that the work done by the gas in a constant pressure process is just going to equal the area under the curve. So if we remember that, well, that's good. Um, and so the work would be negative work gas. We know that we remember this work is really the work the surroundings does on the gas. So we could use that, um, or we can remember that the work for a work gas for an constant pressure process is just going to be equal to P delta V, and so we can just plug that in. And again, that really is just the area under the curve. So that's going to be negative because W surroundings equals negative W gas. And we just said W gas equals P delta V. Okay, so now we have this. And we're starting to get somewhere. So let's bring this P delta V over. And we'll get 3/2 NR delta T plus P delta V. It's going to equal Q. And okay, we're almost there, but we have to deal with this P delta V. So what's that going to equal, and how can we work with that? Well, maybe we can think about the ideal gas law. PV equals nRT. And we think about the ideal gas law in regards to a constant pressure process. So the pressure is a constant, and NR is certainly a constant. So a change in V will result in a change in T. So let's say P delta V equals NR delta T. And so this P delta V right here, let's plug in nRT. So now, for our expression for Q, we have PV equals NR delta T plus NR delta T equals Q. So 3/2 NR delta T plus NR delta T, or 2/2 NR delta T, is going to give us 5/2 NR delta T equals Q. So we can plug in the relevant numbers, and we're going to get a Q of something like 203 joules. And we'll see that is more than 122 joules for the constant volume process. So now I think we're ready to answer our question and say that a constant pressure process is going to require more energy. And if you don't yet believe that work for the constant pressure process is equal to P delta V, we do have one more way that we can prove that. And that's just by looking at the cylinder and thinking about the piston and thinking about the force. There's going to be a force exerted upwards by the gas, a force exerted downwards by the surroundings, and we can think about displacement. So the positive work will come from displacement in the direction of the force of the surroundings, because we know that work equals FD cosine theta. So in this case, where do these forces come from? Well, they come from pressures. And pressure equals force over area. And so what about our displacement? Well, it's going to be a change in height. And how can we know about that height? Because we think about expansions and compressions. This is really a change in volume. And volume is going to equal area times height. So let's see if for work, maybe we plug in Um, we want to know about the force, so the force is going to equal pressure times area equals force, so pressure times area. And then we want to maybe multiply that by D. So D is going to actually equal, and like we said, we're using H. So V over A. And there it is. We can see that these A's will cancel, and work will be PV, and it's going to be a change in V, and P is going to stay the same for this constant pressure. All right, so finally, we want to talk about our conclusion here, and the fact that manipulating these equations like we did in this video is pretty tedious, and we're not going to have to do that in the future if we just want to know how much heat we need to add to raise a sample of an ideal gas, maybe by 1 degree Celsius or 2 degrees Celsius. So we can look at our final Q expression for our constant volume. That was 3/2 nR delta T. And we've made a convenient quantity called CV. And CV is just going to be equal to 3/2 times R. And so that's going to give us an equation that will look like this. Q equals 3/2 NCV delta T. And for the constant pressure, we had Q equals 5/2 nR delta T. And so for this, we can have another convenient constant, and that's going to be CP. So in this case, we're going to have Q equals NCP delta T, and CP is going to just be equal to 5/2 R. So now we can see how this might be something we can work with in the future pretty easily to think about heat transfer to and from an ideal gas. So the specific heat capacity of an ideal gas at constant volume is just going to be CV, and a specific heat capacity at constant pressure is going to be CP.